So hello everyone. As I mentioned just before the beginning, this is not my voice and I'm not trying even to make it funny. I just lost my voice last night. I hope you can hear me at the top. Tim, are we good? Because I can hardly hear myself. So thank you for joining the session on data, specifically on intelligent data mesh. I was asked also to say there is a barcode that you can log in your questions and do some interactions. And I hope while talking a little bit, my voice will become better. If I cough every now and then, I don't have COVID. Okay, it's a normal coughing scenario. And we're far away, which is also fun. Shall we? Okay. So a little bit about myself. My name is Ethan, and I'm the Chief Research Officer of ACCENTURE Labs in Europe. I also run the Israeli location, focusing on applied data and AI, in particular in cybersecurity. This talk is based on a global work that we do across Accenture in the domain of distributed analytics, and that will very soon be linked to the intelligent data mesh. I'm also a professor at the university, and my PhD is in operational research, and the baseline is a multi-degree domain called mechatronics. I'm sure that many of you are not familiar with that term. It's kind of a mesh of the term mechanical engineering, electrical engineering, computer science, and math, all bundled in one. So basically, you can talk any language with me, and I will try to understand, regardless if you're an electrical engineer or computer science guy. The real base for my conversation is around analytics and the implementation of analytics. Particularly, we call analytics generic term, but it's really about smart algorithms, whether they are machine learning, deep learning, normal, linear, probabilistic, I don't care. It's math. For me, everything is mathematical. And the notion of how do we distribute math and how we compute math in a reasonable manner. We'll talk about what is reason. You heard before in the opening conversation with Nick, my colleague, about the metaverse. So Nick and I have been 7 years together, came from IBM. And augmented reality and virtual reality is my passion of implementing data in the space of experience. Just an hour ago, my colleague Fadi mentioned that it's a new domain era of not talking about user experience, but rather talking about participant experience. Cool. No more UX, PX, yet another 2 letters to figure out what they mean, okay? So the way we interact with systems becomes more and more complex. You can find me online and read some of my more passionate patents and more passionate publications for later day. Perception is everything. Do you see a church in this picture? Do you notice the background on this picture? Is there a church? Those of you who are not coming from Bratislava that knows that there is a church, do you think that there is a church? And here's the thing. What you didn't notice is this is a very focused image in the background. Then it was blurring. Then it was night. The data was there, but you didn't see it. We don't see things that we don't intend to. So yesterday, or last week, I saw this cool program from Netflix on infinity. Those of you that like math, do it today. Then, apparently in Bratislava, there is a museum for infinity. Cool. So I went there yesterday. That's the location of the museum, and you see like huge amounts of cabinets and many illusions. And one of the things that really blew my mind is this picture. What you see in front of you is a set of objects and a mirror in which they're reflected on. Please take a close look. Things that looks around in the mirror, they're rectangle. Things that look like rectangle in the mirror, they're round. Look on the arrow in the middle. It points to the other direction. Now, those of you who've been there say nothing. This is not intended to you. It's intended to the people who are not been in that museum, which means you need to go tomorrow. Okay? All of you that like physics and math, that's the place to be. There is no trick. It's a normal mirror that reflects the object. There is no trick. I have nothing under my sleeves, and I just took this picture. Question to the audience: how can it be done? How is it done? What's the magic trick? What is the illusion? So, if it is the angle, how does it explain the fact that you see circles instead of rectangles and rectangles instead of circles and the arrow is flipped? So, maybe on other shapes, but flipping the direction of the white arrow? From 3D to 2D, guys, I was stuck there for 20 minutes. And I'm a mathematician, I'm a physics guy, and it blew my mind. And I was there with my better half, and she started saying, well, there's a trick, it's not a mirror, it's actually a glass. And no, there are no tricks. Here is the beauty stuff. The curvature on top of the object is not flat. When you go down and you take a picture, yes, it's me taking the picture yesterday, fresh out of the oven, so royalty is mine. The top level is not flat. And when you combine your eyesight, the reflection angle on the mirror and the real surface, you're actually seeing different things because the angle and your perspective is different. The object is the same. There's no trick in changing the object. It's just how you look at that. How cool. Yes. Oh, well, they made it into an average person. A child won't get it because they will see it in the angle that there's not enough reflection. They said, it's cool, and they don't get it. That's so funny. How many you go with it? I said, how cool is that? And they said, Dad, that's not cool. It's the same thing. It's not. Why am I saying that? Because one of the key things when we're talking about data mesh, that everybody has an opinion. Everybody talks about the data mesh differently. What I will try to do today is give you my opinion, as to also to emphasize what I'm not talking about. And here is the tricky part. How many of you, just raise your hands, read, heard, talking about a data mesh? Just raise your hand. 1/3. How many just, why did you come to this, listen, this section here? Learning? Okay. When you hear the term data, everybody's fine, that's the name of the track. Okay. When you hear the term mesh, what do you have in mind? Is it a 3D metaverse mesh? A layout of physical space in 3D? Every book on data mesh doesn't talk about the data mesh. They talk about data products. So we are talking about an architecture of a building. Is there something which is called an architecture of a building? Is there something which is called software architecture? No, there's a set of components that are integrated, and we call that integration software architecture. There is a set of data products that somehow nobody talks about the integration, and we call that a data mesh. We are misleading the community. So when I'm talking about what is a smart data mesh, I'm talking about the abstract level of the integration, not about the individual inner elements. It's the same way I will talk about software and software architecture, and will not talk about classes or functions or properties. Let's boost the conversation into decision making. Are we okay? Let's give it a push. So, when I'm talking about an intelligent data mesh, I'm talking about a set of tools, technology, that will accelerate the way to create distributed analytics. The value of joint software architecture is the integration. It's the business process that crosses API over components in software engineering. The value of distributed analytics is having the same thing in the space of data. You're combining data across data sources. Okay? Now, the nifty new term is to call every individual data source by a cool name called data product, because it's not really just a data source. It's something else. It's like writing a function which is private to yourself versus a public function that everybody will use. Writing a component to your code or writing a service that everybody will use. Same applies here. Am I writing a database for my own usage or exposing that for others that I don't know to use my data as though it was a product? However, I'm not going to talk about data product. That's, for me, commodity in terms of research. What I am going to talk about is how to integrate. How many of you have been in some form of software architecture reviews? Raise your hand. How many of you have been in any architecture review? Raise your hand. Are we talking about your functions or are we talking about integration? Are we talking about non-functional properties of the system, quality, speed, resiliency, or are we talking about what this API does? Same applies here. I'm going to talk about the mesh, not the data product. Because you can do a top-down design and you can do a bottom-up design. Developers are doing top-down, trying to reuse bottom-up, which is libraries, ready-made libraries. You are trying to design a software given existing software. Same applies. You're trying to create distributed analytics using existing data sources. And if there aren't some, we'll create some. But that's the end of the game. So, that's my computer. What we are trying to do is to solve it through a life cycle. So, does software have versioning? Do we have versions in software development? Do we have versions in data development? How do we develop data systems? By individual queries or by thinking on developing data systems as though they were software systems? So all of us that came from the software engineering discipline, that's not a new thing, just implemented to the data space. Those of us that came from information systems, purely queries, that's totally new because architecture, software architecture, was never a conversation. But now it is. And it has a life cycle. It evolves, it changes, it mutates, things emerge. Okay? So let's start to get a little bit speed. We are going to weave different components, aka data products. So each data product has its own specific utilization. In order to do that, we need to agree on the API, like we do in software engineering, which means in data, the data schema. We need to be able to convert internal data properties to the interaction data properties, which is known as data transfer objects, the things that transfer on the fly. Remember, we have data at rest, we have data at motion. So we're talking now about data at motion. I'm not going to talk about data at rest, which is the inner elements of a data product. That's data at rest. I'm talking about flows. And I think I'm going to give up and do the simple thing, you know. I'm here. Why I'm doing the clicker? Okay, I have no clue. And we are going to adapt that to the notions of distributed systems. So, a little bit about data architecture. What's better, big data or data lake? Those are your favorite of big data, raise your hand. Those are your favorite data lakes, raise your hand. Those are your favor of data warehouse, raise your hand. Okay? Why none of you is raising your hand? Because depends, right? Different use cases needs different types of data architecture. But then do I need to implement again and again and again different technologies? It costs a lot of money. So can we have a system that can behave as though it was big data, upper left, as though it was full peer-to-peer, bottom right, autonomous system, as though it were recursive, reinforcement learning, AI, upper right, as though it was client-consumer, bottom left, with the same approach for design. So we do not need to reweave everything again and again and again, and we don't need to argue within the organization what type of structure is better. All and none. Depends. I just want to control the integration flow, not the base components. They need to be there. And my job as a designer, as a data architect, is to figure out the weaving flow. But then things start to get wrong. So if you try to do common components in an organization, all of us who has been there know this is, I can't even start saying how many scars I have on my back. Of do this, add that, change that, who's control, who is the owner, what's in it for me? All those arguments, they'll start to killing you because it is difficult to do reuse. It is difficult to manage changes in components. It is difficult to add just another query, but you need to wait 2 years in line because there are 50 people before you that are waiting for the project and you're not paying the best. How can we accelerate that? Why it's happening? Because we are connecting to more and more data. You saw in the evolution in the morning, IoT, more systems, more data flows, but no one refactors the existing analytics. How many are familiar with the term refactor from software engineering? Raise your hand. How many are familiar with the term from Martin Fowler, bad smells? Okay, I like that better because that's kind of not what you should do, but kind of what you need to be aware of. How many of you seen people changing existing data systems, reports, analytics, whatnot, when they're adding a new query? Do they touch history? No. Because they have no understanding on what the history means. So they're just keeping on adding more and more and more. So your analytical code looks like spaghetti. Short comment. I have a paper years ago. As you can imagine, I'm coming from Israel. I have no relations to colleagues in Italy, just friends. Why I'm saying that? Because I have no clue what's the difference between spaghetti and lasagna. And the title of my paper was Refactoring Software Engineering, from spaghetti to lasagna. Same taste, different structure. The term same taste got me in so much problems because they're saying spaghetti is not the same taste as lasagna. For an Israeli guy like me, perspective, it is. So changing just the structure, actually they're saying, no, you're changing the taste. I have no clue what they're talking about. As I'm saying, until this day. But how do we refactor and maintain the taste? Don't destroy anything, just improve the structure. And similarly, the notion is that we need to make the creation of additional analytics on existing systems faster, not slower. Here is the kind of dichotomy in the mindset of CEOs. The more data I will give you to the data lake, the more analytics you can provide. Yes or no? It's theory. Because in theory, I can provide. In practicality, it will take me 10 times more just to produce the same thing, not to deconflict many issues. And that's what we're trying to do. So, lifecycle, we want to simplify and optimize the creation over time, not redo and add spaghetti code. Ontology, versus knowledge graph. Ontology is the data schema in a graph format. Knowledge graph is the data value, the things that you run your query on. If I would be a SQL guy, tabular format, I would say the SQL schema and the actual record sets. In the context of association, ontology is very much like a language, natural language. Something runs on something. There is an expression. When you are going to analyze the structure of the best ontologies, and we'll talk about merging ontologies, merging data schemas, integrating systems, deconflicting data, all the things that you know from your regular data challenges. How do we do dedupe in a knowledge graph environment? How do we do schema matching in this environment of modular ontologies? Modular ontology is a component. It's a data product that has data. How do we merge all this together? Well, you need to understand languages. You need to understand the meaning behind things, semantic knowledge graphs. And deconflict, not just based on the data as we do in normal data systems, but also deconflict based on the associations between the data entities. It's a graph universe because it depicts a conceptual structure of the universe. We now are in a room with X amount of people sitting at is not data, it's a description of what we do. Try to model that in normal tabular form. Try to model that in graph form. What will happen first? So graph is more natural the way it interacts. However, there is a dependency between where are we getting the original data from, how do we structure it, that's the ontology, what type of math we want to extract from it, and how do we want to keep it. The decisions on data products is as same as decision on separate components in your software architecture. Data products, components, same. So I was just returning from Vietnam. The notion that many people told us when we were walking in the bazaars there in the market is same but different. I love it so much. Same but different. Same in terms of how you structure it, but totally different because data doesn't have behavior. Software does. The behavior is in the mesh, in the analytics. So in the data space, we have the data itself and the behavior, which is the analytics. In the software space, behavior and data, like object-oriented programming, is encapsulated in the same environment. So we're going to run through several examples. The first one I'm going to show you is a visualizer on exploration of a data model that interacts with both data products and analytics in the space of retail. Then we are going to see how it works on what we call no-code policy setting in terms of access permissions, who can access what system, when. It's a dynamic nature, it's a behavioral property. And we're going to see an example on sustainability. How do we model different dependencies between data sources for the purpose of computing sustainability challenges? Okay? So let me just swap. Okay. So the first environment is the retail space, as I said. This baby here, let me just increase the size. This is data product that's coming from a certain sensor. This is an ontology element. This is a location where the data resides that is linked to another location where the data resides. And as I start to investigate, I would like to understand what type of analytics runs on what type of server and what type of additional analytics apparently running on that same server. Why? Because when you're changing systems, you need to know who is using that system so you can ensure that it doesn't crashes previous versions. knowing dependency or tracing, as we call it in requirements engineering, is the essence of maintaining systems. And if you are trying to understand, well, that's a cool analytics, but what does it really need? Well, it needs this data. Where else this data needs? Well, it needs another data. And what else that data needs? And it continues and continues and continues. We call that data lineage. The dependencies that either Python code or Cypher code over Neo4j generates between data repositories is dynamic coupling. Again, back to software engineering. We have 8 properties to manage coupling and cohesions between software components. What makes them stick? Why are they together? If I change this one, what else needs to be changed? If I do not know how to do this divide and conquer, I cannot maintain software architecture. Because every time I touch something, I destroy something. Hence the well-famous slogan, which, if it works, don't touch. We have no choice. If you touched, of course it will break. But if you touch, what you need to do? Test. So you need regression testing. Every time you touch, you test. How do you test? Based on the use cases. You run test cases. What is our test cases? The distributed analytics. And if it's not weaved together, should I test all the analytics that I have? No, only the ones that are coupled. So if I don't know the coupling structure, how the heck can I maintain a mesh over data products? This tool gives you the visualization of the ontology and the relations between those components. The notion is, how did I create that in the first place? Because you're seeing an existing system. So let's take another example. That's a beauty. This is a project that we've done for the Future Combat Air System project that is hopefully will commence soon. This is a knowledge graph that shows the properties of different systems that are supposed to collaborate. However, if you're a German pilot flying a German plane, you're allowed to activate all the analytics on the plane. But if you're a Netherlands person flying a German plane, you can only take pictures. The user and the asset, when you couple them, changes access permissions. Who can access what, when? So the first challenge is to model graphically, no code, what can access what. And as we start to evolve the mission scenarios, we can change permission settings, like change, and everybody now have different access permissions. Change, different access permission. The thing is, does it work? So here is the thing. I'm going to try and design, this is for mission officer, this is not for developers. So I'm an officer, I'm designing the rule of engagements in this incident, and I'm saying that a certain plane can, let me just, can access a certain next generation fighter. So I just modeled the fact that I want those two to talk. And I will run a validation plan. And it highlights as red. Why? Because in the policy setting, there is no ability of a certain artifact. In this case, it was a type of plane to connect to another type of plane. That rule doesn't exist. So it says that the interactions that you're planning violate a certain governance rule. So either you add a governance rule that allows that, or you don't do that. It's a compiler and a debugger for the data environment. And just imagine the complexity when you have 7,000 entities. And when you're looking on what type of element I would like to see. That can be the instance level, it can be thousands and thousands of instances. It's not manageable by humans. So it's a graph. It's an ontological graph. So we can run graph neural network to see patterns, to see evaluations, to see structures. They assist to assist the developer saying, well, there's a conflict, there's a bug. And the same way we can do, and I will move forward because I'm aware of time, on carbon emission. So if I would like to experiment and learn more about how a certain KPI systems look like in the carbon emission space, I can investigate and investigate in context, in small portions, and understand my dependency. This is meant for this presentation. When you're looking on real system, if I will show you a graph with 10,000 nodes, remember the beginning? You won't see the castle, you won't see the church. You will focus only one thing in the middle. You won't see the fact it's the same object, you think it's something else. You will have a different perspective on the issue. That's why we need automation. And part of the automation tools, and that's why I'm going back to the presentation, is to think about what do we need to do as data mesh architects. There you go, new profession. Data mesh architects in the lifecycle of system. There is the requirements phase. What is the data model, the domain that I need to capture? How do I blend two domains? If they have the same property, do I need to keep them both or just delegate remotely, federated manner to another data product? Which one will I use? Which API is better, in essence? These are all the things that we think of when we are building ontologies. Most of the data schemas that are out there are not ontologies. They are relational databases. They're not semantic. They cannot really, deconflict because there are a lot of unknown knowledge that the designers inserted that you don't understand. There is no context. When you're doing semantic modeling, you're blending different types of data models. And as you evaluate, the second question will come, great analytics. Can it run on my computer? Data engineers always think about building new databases. Data modelers think about, this is the data schema. Data scientists thinks about math. And systems break down. Because the math guy doesn't understand the schema, which doesn't activate on a certain computer that doesn't work. It's not tangible. So when you're designing a system as a software architect, would you get away from the fact that you didn't put security? There's no encryption, there's no access permissions? Of course not. Why are we letting that fly away in the data space? So as you model data systems, you need to incorporate that with all of those non-functional requirements of the system. And that brings me very quickly, I'm skipping some slides, to the tool set as a whole. On the left-hand side, that's the data sources that you start with, regardless what they are. You want to wind up at the right-hand side with the proper mesh design, which is reusable, extensible, modular, all the attributes that you're knowing and you know from software architecture here as well. So for phases like any classical DevOps, in this case DataOps, 4 cycles. First one is requirements. How do you set requirements engineering for an evolving data grid? It's not just a schema, it's a data grid, which means if you change something, it needs to run under a certain time. If you marry something, there is privacy limitations, you cannot move the data. There are restrictions on the usage of the data. Next step, design. How do you discover what data you can use? How do you compose and marry 2 different types of modular ontologies into a composite ontology and deconflict the differences? With the minimum amount of data, not data lake, not bring everything. Bring only, not all my fingers, only this one, and that's it. for the purpose of analytics. It's difficult. So we have tools to automate understanding where you want to change and recommend that to the designer. Do this, do that. And some person said that's a wise decision. Search. Searching text is not searching graph. Graph search, semantic search, works differently. You can search language only and you get results. You can search with associations, with the context, and you get different results. Because searching a graph database is like searching natural language processing. So you even have another skills there. And it goes on to the deployment. Very important is virtual knowledge graph. That's the ability to query the ontology that will figure out where to go and bring the data, which means you decoupled the space of implementation and the space of analytics. Same way we have RESTful API. We don't care if it's Java or Python. It's RESTful API. How do we decouple data queries from data implementation? Via virtual knowledge graph. And at the end, who cares if it doesn't work? If you could not create the grid and you cannot evaluate the quality of your solution, do we have anomalies in the data? Does anybody uses my data? Why should I keep on maintaining something that nobody uses? Where is my data? That brings us to data catalog, watchtowers, data anomalies. Think about the challenge in constructing a mesh. Where is my data? How is it interacted? Is it good? Who is using that? A single person cannot do that. Can a single person develop software system? So why should a single person develop data systems? But they all need to work on the same agile DevOps approach in software. So they all should work on the same approach in data. That's called DataOps. So to conclude, we need a centralized approach to manage. That's what you've seen the result of it, with many back office services to test and validate the correctness of your design, IDE, integrated development environment, or the data space. And we need to deploy it over a grid that looks the same, because they are all exposing the data in RESTful API in ontological fashion. They're all exposing the data in a knowledge graph format, not in a SQL table. So you can cross different systems. And many vendors out there provide adapters. So do you need to know SQL? Okay, but it's better to know graph analytics, because that is an abstraction layer over the top. And with that, just to conclude, the work on data mesh, the design of software architecture, the design of data architecture is a new discipline. If people are talking only about data products, it's as though they're talking about how to design good API in a single data component. They're not architects, they're functional exposures. When I'm talking about data mesh, I'm talking about the profession of software architecture in the space of data. New world, opportunities, new ways to unlock integration. Questions? Thank you for listening to my sore throat, and I just realized I didn't even drink a little bit, so thank you for your time. There are questions online as well. What about versioning, data architecture, data mesh, how version control, I think version control ontologies, that's what it means. Yeah, I mean, if you evolve ontologies, there are versions. So how do you maintain backward compatibility? One of the things in graph databases, there's the notion of temporal graph database, which means changes over time. Changes can happen with the data itself, the data instance, the knowledge graph, and changes can happen to the ontology, to the data schema. The fact that you're not coupling your data schema to the implementation, it's not SQL Server and Microsoft SQL. It's a graph analytics query that doesn't care about the implementation. it allows the implementation database to grow. So as you add properties or add columns or remove columns, it doesn't actually destroy the database, it adds. So the notion of working with virtual knowledge graph assists in versioning over time. It's actually seamless, much more easier than in those of you who worked with the source-based service-oriented architecture was a big issue about how do you handle versioning and how do you know where to route your query. Here, you don't need your routing to the same database because it has temporal properties. It remembers the past. That's a question that I saw online. Questions in the audience here? So I will pose a question. How many of you looked on graph databases? Who is running graph database today? All the social? LinkedIn? Facebook? Meta? TikTok? Everybody. Why is it not in the enterprise? Why are we still stuck in the same dogma that we created databases 40 years ago? Things changed. So should we in the enterprise space? That's for graph database. How many of you, those who are familiar with graph database, knows how to write graph queries? How many are you familiar with some semantic associations? Not primary key, foreign key, and third rule of normalization. That's ancient. It's the base of learning data. Without it, you don't understand relations. But is it the only thing? How many of you are working with other NoSQL databases? Not just graph, there are many forms. Graph is just one form. The space of data, you have a question? The space of data is beautiful because it's math. And it has infinity. It never ends. So I'm happy because anything that you look which has an infinity future, that's fun. There's no end, so we can have fun. And as I said to my colleague yesterday, what I'm passionate about is go to work and have fun. Because if you're only having fun when you're coming back at work for 2 hours, actually you're miserable. So your full day should be fun, and what can be more fun than solving unsolvable problems? Because then your brain is about infinity. Thank you very much.